Hey guys, we're going to start off the lesson with doing a little recap of some stuff we had done yesterday. So we're going to find the volume of a solid that's generated by revolving. So we're going to have circular cross sections. The region between the parabola and the line x equals 3. About the x equals 3 line. So first thing first, we're going to go ahead and try to shade that region. Next thing I'm going to do is show the axis of revolution here. We're going about this line here, and just by doing that little circle I can tell that I'm going to have a radius that's horizontal. So if I draw in the radius here, okay, we're going to have a horizontal radius, and that's an x distance. And to find that little r, you're just going to do right minus left, and the right value of x is 3. The left value of x is y squared plus 1. It's these x values. So right minus left will get you the correct r value. For volume, you just need to integrate the area. And since we're revolving this about a vertical line, we're going to integrate in terms of y. So we would need to know the bottom y value and the top y value. If this was a non-calculator question, all you have to do is find where these two things intersect. So y squared plus 1 set equal to 3. That's what the two x values equal. So you just set them equal to each other, and you get y squared equals 2. Therefore, y equals plus or minus radical 2. Okay, so we're going to say volume equals negative rad 2 to 2, and because this is revolved, remember that means that the area of each cross section is a circle, pi r squared. So pi, we already determined that the radius is going to be y minus the quantity, or excuse me, 3 minus the quantity of y squared plus 1. That's our radius. Don't forget to square it. And again, at this point I'm more concerned with the setup of the integral, not so much your technique on integrating and using your calculator. At that point you should have enough practice with it. So that's a recap of solids of revolution. And now we're going to take a look at what happens if we revolve this about an axis but there's actually a hole in it. Okay, so it's not going to be solid. So how does that happen anyways? Well, if you take a look at the picture that I've shown here, we've got a graph where this is a shaded region. Maybe we've got a function like y equals rad x plus 1, so it's shifting the graph up by 1, and we're also bounding it by the line y equals 1, and we're going from x equals 0 to x equals 4. Now if I revolve this region, however, around the x-axis, okay, so my x-axis would be going through the shape right about here. You'll notice that there's a hole in it because the axis of revolution, there's a gap between it and the first part of the shaded region. And when that happens, you can think about it like you're going to have a like a donut shape or a washer. Okay, so let me try to get that highlighted a little bit better. Okay, so this is the resulting shape. You're going to have a washer. And if you think back to geometry, in order to find the area of a shape like this, you would find the area of the larger circle, which we know. Okay, the area of the big circle is going to be pi times its radius squared, right? And the radius of the big circle is capital R. And then if you've got the area of a smaller circle, that would be pi times little r squared. So the area of the shaded region, which isn't even a circle at all, is just going to be pi capital R squared minus pi little r squared. Okay? And as long as you integrate the cross-sectional area from beginning until end, and in this case from x equals 0 until x equals 4, that's going to give you the volume of the entire region. So let's go ahead and try some practice problems. Alright, let's take a look at example number 5 here. It says find the volume of the region bounded by y equals x squared plus 1 and the line y equals negative x plus 3 if we revolve this about the x-axis. So the first thing I'm going to do is I'm going to show my axis of rotation here, or axis of revolution. I keep saying rotation. I don't know why, everybody. I'm crazy. Alright, so if we rotate it this way, our radius is going to have to go up and down, okay, which means that we're stacking these together in terms of dx. So the first thing I'm going to do is we want to find the cross-sectional area in terms of x, and we want to integrate this from negative 2 until 1. Those are our x values. Okay, and that's going to tell us our volume. So if you would like to take a look at the shaded region here, let me go ahead and darken that up. We're talking about this little region. And your job, your only job right now until I see you guys again, is to understand why this is going to have to be a washer method. If I start at my axis of rotation and I move up to the shaded region, there's a gap no matter where I am. And that distance is my smaller radius. Okay, that distance is dependent upon the parabola y equals x squared plus 1. So my little radius is x squared plus 1. That's the y value on that parabola. Now I'm going to switch to a different color, because if I start at the axis and I go to the top part of the shaded region, that's going to be my capital R, my bigger radius. And you can see that this is dependent upon the line of y equals negative x plus 3. Okay. Technically I am doing for each radius top minus bottom, but the bottom of the radius is the line y equals 0. So, I mean, you could subtract out that 0 just to be consistent if you want to get comfortable with the top minus bottom idea. Okay, so for my little r, the top of that radius was x squared plus 1, and the bottom radius just the line y equals 0. I don't know if that helps or confuses you. So if you weren't confused before and you are now, just forget everything I said, okay? So if we go back to the volume equation up here, now that we've determined our two radii, we just need to plug them in, okay? The area of any washer is pi capital R squared minus pi little r squared. Okay, so in our case, it's going to be pi times capital R, which is negative x plus 3 quantity squared, minus pi times little r quantity squared. I keep reminding you guys that the square on the outside does not distribute. Okay. However, since both quantities have a pi associated with it, we can pull the pi to the front of the integral. Negative 2 to 1. Negative x plus 3 quantity squared minus x squared plus 1 quantity squared. If you were to do this by hand, you would have to FOIL out each of these binomials. You could combine like terms and then find the antiderivative that way. Okay? But again, at this point, I'm most concerned about the setup of the integral. Alright, now I'm going to have you do this example on your own, but I'm just going to help you get the idea of this one set up. We're finding the volume of the region bounded by y equals x squared and y equals 2x, this time revolved around the y-axis. So, if you revolve this way, your radius is going to have to go sideways, which means you're stacking these like a pancake. So your hint from me is that you're going to have to find everything in terms of y. I will show you your smaller radius. First, let's go ahead and shade the region. We're talking about this guy right in here. Okay, and I will draw your inner radius. axis of rotation, undo, whoa, undo. Let's change that guy. Go away. Okay, let me make the marker a little bit thinner here. Start at your axis of rotation and move towards the shaded region until you hit the shaded region. That's your R value. Notice what it is dependent upon. And now let's do capital R. If you start at the axis of rotation and go until the outermost part of the shaded region, notice what that one is dependent upon. Okay, so I'm going to have you set up this integral, and I will be checking the integral setup. Again, at this point, I'm not checking your ability to find an antiderivative, nor am I checking your ability to plug things into the calculator. The setup of the integral is what we're after. So finish up this problem and we'll check it tomorrow.